Hello everyone, and welcome back to Chem 112. Today we will be discussing ultraviolet visible spectroscopy. We will go over what it is, how it works, and how it relates to quantum mechanics. To begin, let's go over what it is. As the name suggests, it is a type of spectroscopy that focuses on the ultraviolet and visible regions of the electromagnetic spectrum. It uses this type of light to determine the abundance of a molecule within a sample, but it can only determine the concentration of one molecule at a time. This limitation, however, is counteracted by the fact that this form of spectroscopy is rather easy to use and it produces very accurate results. So much so that it is routinely used in the quality control of medicine, water, and products of the food industry.
The image shown is of a UV-VIS spectroscopy machine. The input of the machine is in the middle where the cuvettes are loaded in preparation for this machine to read. The analysis of the samples are done on the left side where they go through and get light shined on them. And on the computer, the quantification and graphs are shown of these samples. So, what are some of the mechanisms that go into UV-VIS spectroscopy to make it work? Well, UV-VIS consists of the ultraviolet and visible light spectrums. Ultraviolet light ranging from 200 to 400 nanometers, and visible light ranging from 400 to 800 nanometers. Excitation and absorption in certain types of molecules can attribute to certain substituents giving off a certain light. Excitation of specific electrons in a group of the molecule that are responsible for the color of the compound, as stated previously, are called chromophores. Substituents that either enhance or diminish this coloring power of chromophores are respectively called oxochromes and antioxochromes. And finally, groups that shift the absorption maximum to higher or lower wave numbers are called bathochromic or hypsochromic, respectively. Molecules that contain pi bonds are able to easily absorb UV light during the spectroscopy process, and the more easily excited the electrons are in the compound, the longer wavelengths of light it is able to absorb. This method of analysis deals with absorption spectroscopy, meaning that the machines that perform UV-VIS measure the transition that the molecules being measured makes between the ground state and the excited state. The image shown is a representation of the process that is carried out during UV-VIS spectroscopy inside the machine. The two lamps send out a light that is bounced against a mirror, the lamps in the example above being deuterium and tungsten. Deuterium is a good lamp for analyzing compounds for ultraviolet due to its low pressure gas discharge. Tungsten lamps have a filament inside them that is heated to a very high temperature, making them glow with visible light, which is used for the visible light spectrum portion of the test. The light is then put through a filter, mainly for the tungsten lamp, because it acts as a prism, shining the light through and emitting different colors, splitting up the different wavelengths of visible light. Then it is put through a monochromator, which transmits a selectable set of wavelengths to be put through the sample. This signal is sent through a beam splitter, separating the beam into two cuvettes, one holding an aqueous sample of the compound, and the other one being a reference, which is normally water. The compounds both reflect and refract light in unique ways, so the inputs are sent through a diode to be processed, and the signals are then outputted onto the graph that is shown on the computer, measuring absorbance of the light versus the wavelength.
UV-VIS spectroscopy is best depicted through the one-dimensional particle-in-a-box model of quantum mechanics. This model defines the arbitrary bounds to the two atoms of the bond in question. This restricts the electron movement to the molecule itself, which allows the bond length to be restricted between the two sides of the box. The value of the bond length from this model is denoted A. On the right, we can see an example of the particle-in-a-box model, where the sides of the box are at 0 and A, and there is an infinite potential outside of the box. In order to correlate the particle-in-a-box model and the measured wavelength that the spectrometer reads, this equation is used, where n is the number of pi electrons in the system, h is Planck's constant, m is mass, and c is the general quantum mechanical value.
Here is an example of a UV-VIS spectrum taken from a milk powder analysis lab. In UV-VIS analysis, the peak maxima are typically the points of interest. In this spectrum, there is a notable peak maximum at 750 nanometers. This can be plugged into the equation on the prior slide to calculate the length of the peptide bonds in question. Here are our references for this presentation. Thank you for watching.